Okay, so let's work through an example here. We've got this journal bearing on a steam turbine rotor. It's got a load 17 kilonewtons, and we're looking to kind of determine some parameters uh, for this bearing. So it's already they've already determined that they want to be working with a 150 millimeter diameter shaft, uh, and that they're going to be using SE10 oil, uh, and working with an average film temperature of 82 degrees Celsius. So, unknown parameters. Not sure what sort of L we're going to be working with. We're not sure what sort of clearance we're going to be working with. Those are things that we kind of need to determine based upon the other parameters. So first off, let's figure out what sort of L we want. So if we go back to this chart here, typical unit load capacity in current practice for different applications. So if we're working with steam turbines, they typically work with a load capacity in the 1 to 2 megapascal range. So again, that's our bearing pressure there, right? Like that's our um, our W divided by L times D. So we know the W here. We know that we know what the D is. We don't know what the L is. So we want that to be within the 1 to 2 megapascal range. So, well, let's just solve for L for those two conditions. So if we solving for L is equal to L is going to be equal to W divided by P times D. So if we have a let's do this for the 1 megapascal one. So if we have 17,000 newtons divided by 1 newton per millimeter squared times a D of 150 millimeters. Again, one of the millimeters cancels out, the newtons cancel out, and we are left with a length of that's 113 millimeters. So that's for the that's for the 1 megapascal condition. If we used the 2 megapascal, the term on the bottom there would double, so we'd be left with half of that, so 56.6. So our L, 56.6 to 113 point, I forget what the point was, times 113.3 millimeters. That would be a reasonably acceptable range for what we're typically using. Now, obviously, we're probably going to want to be using a relatively even number. What we probably want to be using is something that's fairly easily obtainable. So if we want something that's easily obtainable, then we're typically going to be wanting something that has a reasonably round length to diameter ratio. So if we pick a 75 millimeter long bearing there, that'll give us a length to diameter ratio. A length to diameter ratio of 1/2. So that'll be useful for simplicity's sake. It also make our analysis easier because we're working with the hydrodynamic performance charts, and then we can just read it off the line instead of having to interpolate, which can be, of course, a pain in the ass. So let's pick an L 75 millimeters. The next thing that we should try to figure out is what our viscosity is. So we've got viscosity is equal to what? We don't know what our viscosity is, but we do know what our average film temperature is because it's being controlled for that. Basically, they're cooling the when they're recirculating the lubrication. It is being cooled enough that we're targeting an average film temperature of 82 degrees Celsius. So if we go to our chart here, I'm going to zoom in a little bit there. So if we're looking for 82 degrees Celsius, let me see here. Looks like 1, 2. Looks like there's 4 divisions here for each line between 80 and 90. So we're looking at, just to the left of the first division there. So right about there. And we're looking for SE10, so that's the lowest line. So that is, that's going to be on, that's basically in this line right here. So looks to me like, so these divisions here are half increments. There's 10 of them. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so they're half increments. So this value here, that's going to be 6.5. 3 up from 5. So 6.5 is going to be our absolute viscosity. That is in micropascal seconds. No, millipascal seconds. Millipascal seconds. Okay. 6.5 millipascal seconds. Okay, so we know what our well, we can count. We've got our length, our load, our diameter. So let's calculate what our actual P is. We figured out what their kind of acceptable range is. We didn't calculate what it actually is. So 17,000 newtons divided by 75 millimeters times 150 millimeters. That gives us 1.51. So P is equal to 1.51 megapascals. And then we have we got our rotational speed. That's going to be 1800 RPM. Keep in mind that our hydrodynamic performance charts are in terms of revolutions per second. So we need to take that 1800 divided by 60. It gives us, holding my pen upside down doesn't help. That gives us 30 revs per second. Now, when one person asked me a question, I guess it's a bit confusing about when I used radians per second and when I used revolutions per second. When we're working with our hydrodynamics performance charts, when working with these, the N that's used there is all in terms of revolutions per second. They could have scaled it so it was in radians per second, but they didn't. So so be it. But if you're doing any calculations for like power loss or what have you, then essentially you're defaulting back to what you're used to for calculations using radians per second. So that'll I hope that clarifies things, helps avoid any confusion there. So we've got our N, we got our P, we got our U, we've got our radius. We don't know what our clearance is yet. And essentially, though that's the only thing left for kind of determining where we're going to be sitting on our hydrodynamic performance charts. So when we look at this, we're going to be wanting to, when we look at this chart here, especially because it's the one that kind of defines what our optimum range is, our optimum zone is. So if we are operating, we want this thing to be operating somewhere along here. So yeah, somewhere along this line. We're on the length to diameter ratio of half line. So the intersection, the top end intersection there, to me, so just going straight down from this intersection, that brings us down to there. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so that'll be okay. So 10 divisions between 0.2 and 0.4, so we're looking at 0.36 there. So 0.36 is going to be kind of the top end of our optimal range. S max, I'm going to call that S max, or I'll call that S max load, because that's what that corresponds to. X max load is equal to 0.36. And then on the bottom end, so looking closely there where this line intersects, I think we're probably looks to me to be about there. Which should be approximately, I think that'll be about point. Let me think here. From based upon the scale, I think we're looking at about the 0.036 range, 0.037 range. Let's 0.037. Let's go with that one. So 0.037. That's the S for min friction. Now we probably want to be targeting closer to this one than we do for this one. But you know, that's kind of the optimal range. We don't want to go beyond those. So what clearances would those correspond to? So let's see here. So I got to keep in mind our S is equal to R over C squared times the viscosity times the rotational speed in revolutions per second divided by P. So for solving for C is going to be equal to our, let's see, I'll multiply, actually, sorry, forgot, this squared should have been on the outside here, or just R squared over C squared. That works too. Okay, so if we're solving for C, that's going to be what? R squared, viscosity, rotational speed divided by P, SP, and then take the square root. So we got the two options here for those with the two different S values. So our C is going to be equal to the square root of 150, oh wait, no, not diameter, radius, 75 millimeters squared times our viscosity, that is going to be 6.5 times 10 to the negative 6, sorry, 10 to the negative 3, 6.5 times 10 to the negative 3. Let's see, so we're looking for Pascal seconds, so I'm going to put that in newtons per meter squared times seconds times our rotational speed, 30 revolutions per second. We just leave the revolutions out, so seconds cancels out. All divided by our S value. I'm going to leave this there for now because we're going to plug it in for the two different numbers. And our P value, which is going to be 1.51 newtons per millimeter squared. Okay, so what do we got here? We've got our newtons canceling out. We've got the we need to reformat one of the millimeters. So this millimeter on the bottom here is divided out, so we can just cancel that out, move it to the top. Got millimeters squared there. We got meters here, so we're gonna need to convert one of those pairs of millimeters to meters. So times 1 meter per 1,000 millimeters, and then square that, and then that'll allow us to cancel out those millimeters and cancel out the meters squared. So then we are left with a term whose only units are these millimeters squared, and then we take the square root of that. So, and then our S term is non-dimensional, so I'm going to take that out. Our C is equal to 1 over the square root of S times, let's see here, 75 squared times 6.5 e negative 3 times 30 divided by 1,000 squared divided by 1.51. Seven point 7.26 times 10 to the negative 4 millimeters. Oh wait, I forgot to take the square root of that. There we go. My bad. Uh, 0.0269, let's 0.027 millimeters times the times 1 over the square root of S. So for the S value of 0.036, that divided by the square root of 0.36, 0.36, the top one, divided by the square root of 0.36. That gives us a radial clearance of 0.0449, 9, not 8, millimeters. And then for the 0.037 S, that gives us a radial clearance of 0.14 millimeters. So it's a fairly wide range there of values that we could target that would still allow us to be operating within the optimal range. So now that we've got the range of S's that we should probably be dealing with, what we want to do is we want to figure out whether or not we're going to have an acceptable H naught. So whether or not the minimum film thickness that we're going to see is going to be large enough. So flipping back here, the suggested relationship that we should be using is we're working metric here, so we want to be using an H naught that is larger than 0.005 plus 0.00004 times the diameter. So 0.005 times plus 0.00004 times 150. That'll give us a minimum H naught that is acceptable for our condition for this bearing of 0.011 millimeters. So working from that, and the suggested safety factor for that was also 2. So basically, that would be obtained by multiplying the load by 2. So in this instance, this is the condition here where we're going to get the lowest H naught, because again, you'll recall that when we kind of look at our charts here, H naught is going to be so I wanted to have the eraser there. Our H naught is going to be increasing with with our S. So if we take the lower S and then decrease it further by multiplying the load by 2, because again, keep in mind that the P is on the bottom here. So if we multiply the load by 2, then we're going to decrease the bearing characteristic number by 2. So basically, in a condition where we have our S that is equal to that value there, I can't believe I just pointed at my screen, 0.0472 divided by 2, that would have an S of 0.0236. And we want this to correspond to an H naught larger than this. So going back to our charts here, zooming in. So that'll be, let's see, so here's the, I think that'll probably be right about here-ish, which means that we are looking at right about here for our minimum film thickness variable. So that'll be 0.0, let's see, 0.083, I guess, 0.083. That'll be a minimum film thickness variable. 0.083 is equal to our minimum film thickness variable. So that minimum film thickness variable is again h naught divided by c. Right there. So that's equal to h naught divided by c. So in this instance, that is a result of having the this particular one is the result of having the larger the smaller s is the result of having the larger radial clearance. So this is where we're going with the 0.124 millimeter C. So solving for h naught, 0.124 millimeters times 0.083 is equal to h naught. So in that instance, we would actually end up with a h naught that is equal to 0.0102 millimeters. So what do we want to do with this then? So if we weren't able to obtain the h-min that we wanted, then what we might be able to do is tighten up the range of allowable s's by adjusting the range of the allowable clearances. So if we changed our clearances so that they weren't so that we weren't able to get as high of a clearance on the large end, then we might be able to adjust an allowable adjust our allowable tolerances such that they're more within that they result in an allowable an allowable safety factor for our h naught. So for example, if we adjusted the maximum radial clearance that we saw to 0.1 millimeter instead of 0.124 millimeter, that would give us an S value for that actual configuration of 0.1 squared. That would be 0.0726. Divide that by 2 to kind of get our overload condition. And there we would have an S of equal to 0.0363. I don't know why I go to that many decimal places. So if we were going to 0.0363, too many decimal places really for looking something like that up, that's basically exactly where we had the minimum friction line crossing our half L over D line. So zooming in there, we're looking at looks to me to be about 0.11. Yeah, 5 divisions between the two. So 0.11 is our h naught over c for that condition. 0.11 is equal to h naught over c. So solve for h naught by multiplying out the c. The new c was 0.1. So 0.11 times 0.1. Oh, hey. I swear to God I didn't plan this out, but that gives us an h naught of 0.011 millimeters, which is exactly what we're trying to target. So our actual condition without the double of the load would be an S equal to 0.0726. Again, we'd need to figure out what sort of tolerance ranges we'd need to work with. So that would be, we need to pick some sort of tolerance combination that would result in a maximum radial clearance of 0.1, and we still want to be working with a minimum radial clearance, not necessarily this one here, but we want it to be our minimum radial clearance would need to be based upon having an having the within the optimal zone. So we still want it to be within the 0.036. So at let me just double check. So at that radial clearance, we have 0.045 millimeters is our minimum. C min equal to point. So figure out some sort of combination of the tolerances on your hole and on your shaft that result in a minimum and maximum radial clearance of those values. Obviously, typically speaking, when you're specifying tolerances for a shaft, you're working with diameters. So just multiply that by 2, and you'll get something suitable. So something within that range should work to still attain our H0 minimum. If you didn't want to change the clearances, you could also adjust some other parameters. So you could, for example, use a different viscosity of oil. You could you could provide more cooling to the oil, so that the oil that you do have coming in is going to end up being at a higher viscosity than based upon the average temperature in the bearing that was specified of the 82 degrees Celsius. So you could use different oil, you could use a different temperature, or what have you. So, but that would work. So suitable. We figured out kind of what would be a suitable combination of bearing length and radial clearance. So a range of radial clearances, really. So let's figure out what the corresponding values of the coefficient of friction are, and then the friction power loss and our oil flow and oil temperature raise. So our coefficient of friction is going to be found on this chart here. So we are going to get coefficients. We'll do it for these. We'll do it for this value here for S, and we'll do it for an S of the 0.36, which is where it crosses the line for the maximum load. So the coefficient of friction is again a function of the S, and in this case they're giving it in terms of the radius divided by the clearance times F. So looking up what we should be getting for the 0.36 value, which is going to be again a higher value than what we're looking at for the minimum friction condition. Got this line right here at 0.36, and that intersects with our half load line, or half LVD ratio right here. Let's make that thing flat, actually. There we go. So that looks to me like we are at 1, 2, 3. Looks like we're at 9. So 9 is our R over C times F. So we got an R over C F of 9. That was, again, for the S is equal to 0.36 case. So that is the one that corresponds to the smaller clearance. So that's the minimum clearance value. So solving for F is equal to 9 times 0.045 millimeters divided by our R. So 150 divided by 2, the diameter is 150. Radius is therefore 75 millimeters. So what does that end up being? That gives us an F value of 0.0054. So the next one we need to do is the one that corresponds to the S value of the 0.0726 or 0.072. So looking at this chart here, we're looking at about 2.8 for our coefficient of friction variable. So 2.8 is equal to R over CF. So solving for F, 2.8 times, that was the one with the C, our C max basically is 0.1 millimeter for our radial clearance. And then the radius again is 75 millimeters. 2.8 times 0.1 divided by 75. That gives us 0.0037. And this one is for an S of 0.073. So that's our coefficient of friction range if we're using those radial clearances. So our minimum that we could see is 0.0037. Our maximum that we can see is 0.0054. So, reasonable difference between the two, but not orders of magnitude different at all. So the next thing that the question asked of us was to figure out the power losses. So again, just a reminder, kind of how the coefficient of friction variable, the coefficient of friction was defined, is basically allowed us to figure out our torque. Our torque was equal to the load times the coefficient of friction times the radius. So let's just do this in kind of columns, I guess. So over here we're going to have the S is equal to 0.073. Over here, let's do the S is equal to 0.36. So the torque the torque caused by the friction in this scenario would be equal to, load stays the same, 17,000 newtons times 0.0037 times the radius, 75 millimeters. Actually, let's put that not in 75 millimeters. Let's put that in meters. 0.075 meters. I forgot to put the newtons on there. So 17,000 times 0.0073 times 0.075 meters. That gives us a torque caused by the friction of 4.7 Newton meters. So that's a torque we need to overcome if we want to figure out the power loss. That's going to be equal to the torque times the speed in radians per second. So again, the charts are all in kind of normalized to revolutions per second, but if we want to be doing power calculations, we need to do that in radians per second. No, I'm not sure why they didn't just normalize the charts for radians per second instead. Who knows? But we've already torque times our rotational speed in rads per second. So 4.7 Newton meters times 30 revolutions per second times 2 pi radians per rev. That gives us 4.7 times 30 times 2 times pi is 886 Newton meters per second, or watts. So that's for this one here. That's our low friction case. For our high friction case here, we got what do we got here? So the coefficient of friction is 0.0454. So realistically, the only value here that changes is the coefficient of friction. So the calculation remains the same, other than the fact that this thing got multiplied by a slightly different value. So what I'm going to do here is I'm just going to say that the power loss can be calculated. I've got the 886 times the ratio between the two coefficients of frictions. So times 58 divided by 32. So in this case, our power loss is going to be 1.3 kilowatts. That is a terrible W. There we go. That's a bit better. 1.3 kilowatts versus 880 watts, 890 watts over, suffice it to say, when we're reading these values off the charts, we're making a lot of guesses on the exact value. Our significant digits are fairly low, so you don't want to be throwing too many decimal places behind all of these. So that's our power loss there. So next up, oil flow rate. We are, again, let's start with the high S value here. So we're looking at the line, let's see, looking right here. And we're looking at the intersection here. So that one looks to me to be 4.8. 4.8 is going to be our flow variable. And again, that is equal to Q over R NCL. So solving for Q, 4.8 RNCl, 4.8 times 75 millimeters times 30 per second times C. So the C that corresponds to that one, that is our 0.045. And then our length is also 75 millimeters. So 4.8 times 75 times 30 times 0.045 times 75. That gives us 450 millimeters cubed per second. Let's have a look at what the side flow would be for that case. So let's see here. So we're looking here, this line here. There we go. And we're looking right about here. So looks to me to be about 0.73, let's say. .73 is equal to Q side over Q. So Q side is equal to 0.73 times the value we had just previously calculated. So 26,600 millimeters cubed per second. All right, and then let's do the same thing for the other case. The S is equal to 0.073. So we're 0.072, and we're looking at 1, 2, 3. We're looking at about right here. And we're crossing the line there. 1, 2, 3, 4, 4.5. So now let's say 5.5 just to round off a little bit. So our Q is going to be equal to 5.5 times RNCl, which is equal to 5.5 times 75 millimeters times 30 per second times the clearance for this one was 0.01 millimeter, and the length is the same at 75 millimeters. So 5.5 times 75 times 30 times 0.1 times 75 is equal to 92,800 millimeters cubed per second. So not surprising, it's a fair chunk larger than the other one. A lot more clearance. it's got less friction because it's got more stuff going through. All right, so our side flow in that case, again, let's see here. Looking at about there. So an intersection at right about there. 0.9. So our side flow is going to be equal to 0.9 times the Q. So 92,800 times 0.9, 83,500 millimeters cubed per second. So what else does the question ask of us? Oil temperature rise through the bearing. So we got the yeah, as for the oil flow rate to and from the bearing, so that's that's going to be the side flow. So any of the stuff that gets recirculated stays in there. Any of the stuff that comes out needs to get recirculated back in. So the flow rate to and from the bearing is that, those side flows. So the oil temperature rise through the bearing is based upon it's basically based upon the side flow. So basically, what we can assume here is, well, okay, so it's temperature rise is based upon the flow rates and the what you call it, the heat generated by the friction. So you got to keep in mind, if we're gonna get a certain amount inward, and then some of it gets recirculated back, basically you're gonna get the oil from the inlet mixing so that it brings the average temperature down enough, so that when it mixes with the oil that's recirculating, it's low enough so that the average temperature for the entire process is going to be equal to 82 degrees. Basically what that means is that the oil that gets recirculated, let's assume it's the same oil. It's not actually going to be the same oil, but it's going to be the same volume of oil. So if the oil that gets recirculated, it's going to get recirculated. It's going to come in, and before it starts to mix with the side flow oil that's returning after being cooled, it's going to be at it's going to be at the outlet temperature. So it's not going to change its temperature during that process. So it's going to come out, go back in at the same temperature. So we can kind of neglect basically that recirculated oil kind of stays at the same temperature, and it's the side oil that we need that needs to account for all of the cooling required. So that cooling that's required is going to be so we know how much heat's generated. So all the heat needs to go into that into cooling that how do you say, all the heat that's generated needs to go into heating that oil, and then that same amount needs to cool down so that everything gets back to steady state. So we've got a certain amount of side flow, and we have an inlet temperature, and we have an outlet temperature. And the average value of all of the oil that, sorry, let's see. So the average value of the temperature of the oil in the hydrodynamic wedge is 82 degrees. Now that's the average of everything. So that includes the, that is basically the average temperature of the mixed portion of the recirculated oil and the stuff that had been cooled, and then the outlet for everything. So if all the cooling, if all of the actual removal of heat from the bearing is done by the side flow, then basically we can use that to calculate the temperature change between the inlet and the outlet. So the power, kind of the power dissipated loss, power loss is going to be equal to the side flow times the temperature change times the specific heat capacity. So again, you'll recall that the specific heat capacity that was mentioned for typical lubricating oils, as in one of the previous lectures, was 1.36 megapascals per degree centigrade. So if we want to solve for the temperature change, that's going to be equal to our power loss divided by the side flow and the specific heat capacity. So plugging in our known values for that, our power loss for this scenario was 1.3 kilowatts, 1300 watts. So again, I'm going to put that watts, I'm going to put that in its more basic terms, Newton meters per second. And then I'll divide it by our side flow. So 26,600 millimeters cubed per second. And we got per seconds on the top, we got per seconds on the bottom. I'm just going to cancel out those per seconds. And the specific heat capacity. So 1.36 MPa per degree Celsius. So I'm going to put the MPa in terms of newtons per millimeter squared. And then degrees Celsius at the top here. So this cancels out 2 of the millimeters on the side flow. The newtons up here cancels out. And we are left with a meters per millimeter term here. So what we need to do is we also need to multiply this by 1,000 millimeters per meter. Oh, I realize I'm writing off the screen for what you guys can see here. So that meters cancels out, our millimeters cancel out down here, and we're left with a delta T in terms of degrees Celsius. So 1300 times 1000 divided by 26,600 times 1.36. That gives us a delta T of 36 degrees Celsius. So yeah, that's going to be the change between the inlet and the outlet temperature. So if we want to figure out what the inlet temperature and outlet temperatures are, we need to just keep in mind that the inlet has a certain portion that's coming in at the outlet temperature based upon the fact it's recirculating, and it's got a certain portion that gets cooled by that amount. And then our average in the middle is 82 degrees Celsius. So for the math on that, we take our outlet temperature. Let's call that T hot. TH is our outlet temperature plus our inlet temperature, which is equal to a certain portion that is at the TH. So that portion is equal to the 1 minus our side flow ratio. So 1 minus our 0.73. So that'll be 0.27. 0.27 TH plus our side flow ratio times TH minus 36 degrees. All this averaged together is equal to 82. So adding stuff together, we get, let me see here. Let's add up the THs first. So we've got 1 TH plus 0.27 TH plus 0.73 TH. That's 2 TH divided by 2. All right, so we get TH, and then the non-TH term there is 0.73. Oh, yeah, I realize I'm covering it up. 0.73 minus times negative 37. Oh, sorry, 36 divided by 2. So TH minus 13 13 degrees is equal to 82 degrees. So 82 plus 13, that gives us a TH of 95 degrees, 95 degrees, and then our inlet temperature, therefore, TC for cold, is going to be 58 degrees. All this in Celsius. So yeah, that's not an unreasonably hot temperature that's reaching, but if it starts getting too much higher, then we might want to consider using a different configuration in order to decrease the amount of well, yeah, in order to essentially, we're probably going to want to be trying to target a lower coefficient of friction, so we're generating less heat in this bearing. Or possibly what we could do is instead do something that would increase the flow. So then if we're increasing the flow, then we're getting more lubricant flowing through, and thus the temperature rise needed per unit volume is going to be less. So you're going to get less you're going to get a lower maximum temperature that arises. So that was for the S is equal to 0.36 version. So let's do it for the other one. We've got our power loss again is equal to Q side times delta T times CP. So our Q side there is 83,500, and our power loss was 886 watts. So in this situation, we expect to see a far lower temperature rise because we both have more side flow and we have less heat being generated. And that should be expected with this because it's got a lower, it's less tight of a bearing. So we're not going to be burning as much energy due to the viscous heat. So our delta T, that's going to be equal to 886 Newton meters per second. And I know that I'm going to have to convert that meters to millimeters. Meter, okay. All divided by the side flow for this case, which was 83,500 millimeters cubed per second times our CP 1.36 Newton per millimeter, newtons per millimeter degrees Celsius. Sorry, newtons per millimeter squared degrees Celsius. So our millimeters all cancel out, our seconds all cancel out. When we divide the C over here, it goes to the top. So once we plug these numbers in, it's going to be in degrees Celsius. So 886 times 1000 divided by 8,350 divided by another 1.36. So here we're looking with a temperature raise of 7.8 degrees Celsius. So significantly less. So again, do the same calculation that we saw here. We're going to have a TH plus so the TH's there cancel out, so we're just left with the delta minus delta T times the side flow ratio. So I believe the side flow ratio is 0.9, so plus a negative 7.8 degrees Celsius times 0.9 is equal to 82 degrees Celsius. So let's see here. That gives us a TH of 89 plus 7.8 times 0.9. So our TH is equal to 89 degrees Celsius, and therefore our TC our TC there is equal to 81 degrees Celsius. So yeah, there we have it. Yeah, that is how you go ahead and calculate those. So yeah, that's all. I believe that's all the question asked for. So there we go.